The following is a production of the University of Minnesota.
Okay guys, well today we're going to talk to you guys a little bit about wind turbine foundation engineering. But before we get started, we'll do a little bit on introductions. How do I move back and forth between slides? Oh, down, up and down, got it. Or the other down button. There we go. Okay, so a little bit about introductions for ourselves. There we go. Are these all these are PDFs, so I'm wondering if it's gonna have to scroll through each one. Maybe I'll hit page down, if there's a page down. Sorry, I'm a Windows user. Everybody here seems to have Macs. Is there a way to get this to fit the screen?
It should be. It doesn't have to usually. I usually just go. No. Oh. There. Oh yeah. Sorry about that.
No problem. Technical difficulties. So my name is Rob Osborn, and I'm a geotechnical engineer. I work for Barr Engineering Company. I have a bachelor's and a master's degree here from the University of Minnesota. I've been practicing consulting engineering for about 9 years now. I am a professional engineer. That means I'm licensed to practice engineering, and I'm licensed in the state of Minnesota here, as well as 5 other states here in the United States. Well, we do a number of different things at Barr Engineering Company. A lot of what I've been involved in is wind turbine developments. And my role as a geotechnical engineer is to handle all the geotechnical engineering aspects of these projects, as well as act as project manager. And to date, I've worked on over 50 different wind projects across North America. To add to that, I've also been involved in the foundation settlement research for the Umar Park wind turbine. I'll hand it over to Jenny temporarily here.
All right, I am Jenna Entwistle. I'm another employee of Barr Engineering Company. I've been with Barr for close to 7 years now. Came fresh out of school, graduated here with a BS in civil engineering, the structural engineering emphasis. And I am also a professional engineer, just in the state of Minnesota, though. Most of my work has also been around the wind turbine projects. My focus has been designing the foundations, which is what we're going to be talking about today. So I pretty much started doing that as soon as I started at Barr, and that's been a majority of my project work. I put it that I've worked on over 50 projects, but I really honestly have not counted as far as what I've actually done. It's been in different capacities, but worked on many, many projects. And then I'm also was the project manager for the Umar Park wind turbine project, and I'm also involved in the foundation research for that project.
Back to me now. A little bit about Barr Engineering Company. It says here that we're over 600 engineers, scientists, technical specialists, and support staff. This is actually outdated. We've been growing so much lately. I think we're close to 700, if not. Yeah, it's like 695 engineers. We're headquartered right here in Minneapolis, Minnesota. We're an employee-owned company, and we do have other branch offices. We have 2 in northern Minnesota, in Duluth and Hibbing. We also have an office in Ann Arbor, Michigan, another in Jefferson City, Missouri, an office in Bismarck, North Dakota, and then most recently we developed an office in Canada, in Calgary, Alberta. A little bit about Barr Engineering Company and our experience specific to the wind turbine or the wind industry. We've been working on wind turbine foundations since 1992, which is not quite the inception of the wind industry, but outside of California, there wasn't much going on in the wind industry prior to the early 90s. So we got our start in 1992. Since then, we've worked on nearly 250 different currently operating wind power developments across North America and points beyond. To date, if you look at the total U.S. wind capacity and the number of turbines that are sitting on the foundations that we designed, that capacity, the portion of the capacity on our foundations is approximately 40% of the entire U.S. capacity. So I would say the majority of, or we have more foundations out there than any other engineering company here in the U.S. Looking at the graph there, well, we started in 92. Things didn't really start to pick up until 98. From 1998 to 2004, we worked on almost 1,600 megawatts of wind power. Things picked up in 2005, and we worked on 1,600 megawatts in that year alone. Same thing in 2006. The wind industry kind of kicked itself into high gear in 2007, and we worked on over 3,500 megawatts of wind power in that year alone. Things subsided a little bit, but stayed fairly strong. 2008, 9, and 10, 11. I mean, we're in the mid 2000s for megawatts in terms of power. And this year, in 2012, even though we're not done, we're already over 3,500 megawatts. So we could surpass 2007 in terms of the amount of work we did this year. So wind has, we've seen a substantial increase in the amount of work that we've done in the wind industry, specifically in 2007 and most recently here in 2012. As far as our geographic presence, this map is something that we constantly find ourselves changing, but it shows various states in the U.S. shaded in different shades of green. With numbers below them, a little bit hard to see here, but it just shows the different projects that we've worked on in the United States and points beyond. The darker shades of green are states where we've done more projects. So just a few things to look at here. I mean, if you look at where the Mississippi River is in the United States, we've worked in every single state west of the Mississippi River with the exception of Arkansas and Louisiana. And for that matter, we've essentially worked in almost every single state except the southeast corner of the United States, with the exception of a few in the New England states. But looking at the major states for wind, you see Texas is a big one. Minnesota and Iowa are also big states for wind. This is no surprise, and we've done quite a few projects there. Another big state is California. We've done quite a bit of work in Oregon. But beyond that, we've done some work in the New England area and the Northeast. We've also done work up in Canada. It's hard to see, but there's a little X way up there in the corner of the screen up in Nova Scotia. We've done projects there. We've done a number of projects in Ontario. We've also done projects in Alberta and British Columbia. And looking in the lower left-hand corner, we've done a few projects in Hawaii. Those are always fun ones to work on. We did one in Chile, in South America, and we did at least one in Puerto Rico as well. So we've worked predominantly in North America, but we do a few projects points beyond. So in addition to the foundations that we designed for wind power developments, we do have other wind experience in the wind industry. We've worked on over 200 other projects that don't currently have our foundations. That includes over 100 different projects where we've completed preliminary foundation design. So preliminary foundation designs are designs that we develop for folks to use to develop pricing estimates and use for the bidding phases of projects, but they're not actually designs that would be used for construction of a wind power development. We've worked on over 70 desktop studies where we're looking kind of at the feasibility level evaluation for our clients, and we're looking at civil and geotechnical factors at a project site to see if a project is viable, worth their money to invest time and effort into building a wind power development. We've completed over 100 geotechnical investigations in support of wind power developments. We've worked on over 50 road designs for the civil layout. We've performed at least 28 independent reviews of other consultants' work. We've done a few projects where we've worked on environmental studies and permitting aspects. And then we've done more than 50 now structural evaluations and studies of currently operating or turbines that are having problems. So just some impressions on wind turbine foundation. When you think of a wind turbine, the foundation is not typically the first thing that comes to mind. The foundation is largely below the ground surface, so even if you're working on an operating wind power development and you drove up to a wind turbine and saw this, you'd see the base tower, you'd see the transformer there, you'd see a series of anchor bolts right at the base of the tower, and then a circular concrete pedestal right at the base of the tower itself. The question is that the foundation? Well, it's a pretty large, the turbine is a very large machine, and a simple little concrete foundation like that is not enough to support a turbine due to the static and dynamic loads applied to the foundation. So the question is, what really is the foundation for a wind turbine? Just looking at a schematic here, you can obviously see the tower and the wind turbine itself. The foundation is that component that's below the ground surface right at the bottom of the picture here. The foundation is typically a big mass of concrete with reinforcing steel that spreads out laterally below the ground surface, typically on the order of 50 to 60, sometimes 70 feet in diameter. So we're talking a substantial amount of concrete and steel to construct these foundations. And then the foundations do have a pedestal that extends up to the ground surface. So on the previous picture, that's kind of the top extension of the pedestal that you see right along the ground surface. So that is part of the foundation, but it's just a small portion of what we're seeing in terms of the wind turbine foundation. Because you've got the loads from the wind turbine transferred through the tower, the wind turbine foundation is the most heavily loaded element of the entire wind turbine system. And because it's the most heavily loaded element, it has to be the most reliable and therefore the most robust component of the entire system. So the foundation design, while it's not something that people typically think about, it's definitely a critical component to a wind turbine, and it's not something that somebody wants to mess up. We don't want to have a wind turbine falling over. So just talking about some of the objectives that we'd like to accomplish in today's presentation. We want to help you guys just gain an appreciation for the different factors that go into the design of a wind turbine foundation. So we'll talk a little bit about some of the terminology. We'll discuss how it's an integrated process with a number of different components that play into the actual design. A number of those components are listed here. There's structural loads that come from the wind turbine manufacturer. There's geotechnical engineering aspects of the project that I'll talk about later. There's the actual foundation engineering and design that goes into that, but also considerations for constructability aspects of the foundation, and also, applicable building codes and local and state regulations that govern how the design needs to be completed. And then lastly, Jennifer will talk a little bit about a case study and an example for you guys. So to really appreciate the process that's involved in the wind turbine foundation design, you have to understand that there's a number of different people that interact. It's not one single individual that develops the wind turbine foundation design. You've got the wind turbine manufacturer and their engineers that they have on staff. You have the engineer that's designing the tower that supports that wind turbine. You've got the geotechnical engineer that's evaluating the soil and rock and groundwater characteristics at a given project location. You've got the foundation designer that's creating the design, but you've also got the contractor that's got to find a way to build this project. So all these different entities play in together to develop the actual foundation design itself. So as we mentioned, it's an integrated process with a number of different factors, and I've already touched on some of them, but I'll kind of go into a little bit more detail here on this slide. We've got the foundation in the middle that's kind of simulating the design of the foundation, but we've got a number of different factors, 6 of them listed here, that all play into or are all critical to design of the foundation. I think first and foremost, you've got physical elements in the world. You need to have wind. If you don't have wind, why are you putting up a turbine? That's obviously important. The wind ties into some mechanical and electrical factors. You've got to be able to convert this wind to power. So that's what the wind turbine manufacturers specifically focused on, is optimizing that wind turbine to get the most amount of power out of the least amount of wind. Other physical elements, things like the earth itself, what type of soil, what type of rock do you have at your site? Where's water? Where's groundwater located? Other things like temperature. When it's really cold out, you have frost issues, so you're looking at how do you accommodate for frost in your foundation design. And those things plus other factors kind of tie into what we call the geotechnical factors that play into the actual foundation design itself. And those are very critical elements that the foundation designers take into account when they're building or designing their foundation. Jumping to the other side of the slide here, there's structural factors. So as I touched on earlier, the wind turbine manufacturer, it's their job to convert the wind to electricity. But in doing that, there is a substantial amount of load applied to the wind turbine tower, and that load is transferred down through the tower and applied to the foundation itself. So the foundation designer is evaluating and working with those structural factors, looking at what types of materials are suitable for a typical design. A typical spread footing foundation design, which is the predominant foundation system used here in the U.S., is generally composed of concrete with reinforcing steel. But there's other factors like geographic factors. In certain parts of the country, concrete may be a lot more expensive than steel, and vice versa in other areas of the country. So the foundation designer may be working on ways to use less steel in one area and more concrete in other areas, and so forth. And then beyond that, the foundation designer is just looking at the constructability aspects of a project and working typically in close contact with a general contractor that's in charge of building the foundation and making sure that the design is developed in a manner that is easy for the contractor to build and will generate fairly limited risk during construction. Touching on some of these factors, we've got the mechanical to electrical component. This is the obvious one that we all see. How do you get wind to electricity? Well, the wind blows on those wind turbine blades, causes them to move. They all rotate around the central hub. That hub is tied into a main shaft that goes through the nacelle of the turbine in the back there, and that main shaft is tied to a gearbox, which is then tied to a generator, and that generator is what's converting the wind ultimately to electricity. Beyond that, wind turbine developers, they're looking for sites that have good wind resources. So here's a map of the United States with different shaded areas. The different colors represent different wind speeds. Looking at the map here, it's obvious. You can see the West Coast offshore has a substantial amount of wind. The East Coast has quite a bit of wind, as we can see in the red there. There's a lot of wind blowing across the Great Lakes, and even in the Gulf of Mexico, there's a fair amount of wind. But this is all offshore, and offshore has its own set of complications and issues. Today, we're just going to talk about onshore wind. But looking right in the middle of the map, we've got the Great Plains, and what's the first thing you think about when you think about the Great Plains? It's wide open space and a lot of wind blowing across basically nothing out there. This map it's very evident. The Great Plains on this map you can see stretching all the way from central Texas on up into North Dakota and Montana. It's a huge swath of the United States where there's generally very consistent wind, and that even extends into southwest Minnesota, which it's a little bit hard to see in this map, but when you look in the southwest corner of Minnesota and the northeast corner of Iowa, there's those shades of pink and a little bit of purple, which are fairly consistent winds. You also see a good amount of wind. It's not high wind speeds, but consistent winds in the state of Illinois. It's no surprise. These are all states that we've worked in quite a bit on other wind projects that we've worked on. There's also certain pockets of California. I mean, California is largely devoid of wind until you get to certain areas where it's just blowing like crazy out there. These are all areas that we've worked in. So I'm going to hand it over to Jennifer temporarily here, and she's going to talk a little bit about the structural loads that go into the design.
Rob's a geotechnical engineer, so I didn't make him do this part. So just talking about the structural loads on the foundation, they are very unique in comparison to other structural projects out there. It's not a building, it's a dynamic structure. So what's so unique about this is the overturning moment. So just a refresher, maybe for those that haven't taken physics in a while, overturning moment is force times the distance. So we have the force of the wind hitting the blades, and then that gets translated through the moment arm, the hub height of the turbine to the base of the foundation. What's so unique about wind turbine foundations is that or the wind turbines is that there's a really high overturning moment in comparison to the weight of the structure. So there's not a whole lot holding it down. So we need to design our foundation to resist those loads. So one thing about these overturning moments is it really depends on the turbine type that we're dealing with. There are a lot of different turbine types out there, and also the wind speed that we're dealing with. Generally across the United States, it's pretty consistent, but there's different ratings for these wind turbines and different speeds that we need to design for. So some of the wind turbine manufacturers, listed them out here, but there's more and more that keep coming. Some that aren't listed here are ones that are emerging from China. They've been getting into the U.S. wind industry here. But we get our loads from the turbine manufacturers, so they develop a wind turbine load document that we get our loads from them. Part of what they do when they're going through the design of the turbine and the tower is to run through these different load cases, and so we really rely on them to get our loads. So the turbine load document, what's in that is a series of different loads that we need to take a look at. So the wind turbine manufacturer has a variety of different load cases that they run through. Those load cases are from the IEC, so International Electrotechnical Commission. So what we're most concerned about as far as our foundation design are the extreme loads, both normal and abnormal loads, a normal operating load, as well as fatigue loading. So the extreme loading, there's two different types there. I called it more of a normal operating load. That's really when the turbine is producing power, it's in operation, it's got the wind speed that it's been rated for. It produces an extreme load in that case. There's also what we call an abnormal extreme load. That's something that's more of a unique situation. So it might be if there's an electrical fault and the turbine shuts down. It might be in a situation, as I said, these turbines are only rated to a certain wind speed. So once it reaches that wind speed, the blades feather out of the wind, and so it might shut down in a case like that. Maybe there's a hurricane wind coming through or something like that. So those create extreme load events as well. Both the abnormal and normal extreme loads, we apply different load factors to those when we're doing our designs to just account for what's more common and what is more of a unique event. But we'll get into that a little bit more later. So these extreme wind events are a 1 in 50 year occurrence that we're designing for. We also take a look at the normal operating loads for the wind turbine. So this is really the load that the wind turbine sees most frequently when it's in operation. So that's actually a 25 meter per second wind speed with also accounting for some gust loading in there. And then we have to take a look at fatigue. These are dynamic structures. I mentioned some of, I guess, what we consider more static loading. We take those extreme loads and we consider it a static load, but there's that dynamic wind that's constantly hitting this wind turbine and then getting translated to the foundation. So we need to take a look at fatigue. So fatigue is really that cyclic loading. It's an oscillating load. It's shown on the diagram here, but it's the constant loading and unloading of the structure. So what we get from the wind turbine manufacturer in the load document is a fatigue load spectrum. So that takes a look at, over a 20-year life of the turbine, what kinds of loads is that turbine going to see. So it takes a look at, maybe there's really high loads, but it only occurs a few times in its lifetime, or maybe there's lower loads that occur more frequently. So we take a look at that and compile that. It's the fatigue load spectrums can't get quite large, and we have to condense that into something that we can actually use in our wind turbine foundation design. So I'm going to pass it off to Rob again to talk about the geotechnical side of things.
Okay, so we talked a little bit about converting wind to energy. That's obviously the primary function of a wind turbine, and then Jennifer touched on structural loads. Obviously an important part of the foundation design, but back to just the physical world, we want to look at the geotechnical aspects of a site. And geotechnical engineering is not something that people typically think of when they think of civil engineering. But geotechnical engineering is basically assessing a site for the different characteristics of the soil or rock at the site, evaluating the strength and compressibility of those components, looking at where groundwater is, and developing characteristic parameters for the materials present at the site for the foundation designer to use. So as part of our typical geotechnical evaluation of a wind turbine development, we're first looking at the geology of a project site. So we're looking at what types of soil, what types of rock are present at a given site. We're looking at how the material formed in terms of its geologic sense. And we're looking at factors like weathering of soil and rock, as well as erosion near the surface. And that kind of ties into things like temperature, wind, as well as water. And then also looking at, other reasons, how the soil formed. We're looking at the depositional history of a soil. So some soils are deposited by glaciers, some are deposited by wind, others are deposited by water, like in a river basin. And understanding the geologic history of a soil is a critical role in understanding how that soil is going to behave and how it's going to be able to support a wind turbine foundation. So again, looking at the geology, things like pressure and time are important. You have glacially deposited soils that have seen the weight of a glacier. So the weight of that glacier, the pressure from a glacier over an extended period of time is going to lead to soils with specific characteristics that are very desirable for wind turbine foundations. Looking at the figure on the map here, this is a little bit hard to make out, but it's southwest Minnesota. You can see dashed lines for the border of the state of Minnesota, kind of running down the left side of the picture. The northern edge of Iowa is present at the bottom of the picture. You can see most of the eastern side of South Dakota, a little bit of North Dakota, and then way over in the central part of the right side of the picture, you can see Minneapolis and St. Paul on the border with Wisconsin. It's a generalized schematic showing the recent geologic history of the soils in the southwest corner of the state of Minnesota. Right in the middle of that picture is something that says Des Moines lobe, which, unless you know what it's talking about, it really is meaningless. But here, it's different names for the various geologic units or different geologic formations in the soil deposited in southwest Minnesota. The Des Moines lobe is associated with a specific arm of the glaciers that were over Minnesota as recent as the last 12,000 years, and the lobe kind of corresponds to the type of glacial till or material that was deposited after that glacier left. So you can imagine, if you can imagine, there was a big, huge glacier sitting over a big part of southwest Minnesota, all over that entire area where it says Des Moines lobe. And as the glacier is moving, picks up a lot of sand, silt, clay, gravel, rocks, all this kind of debris is piled on the glacier and is within the glacier. As the Earth came out of an ice age, or out of that ice age, the glacier receded and melted in place and deposited all that soil that was sitting right on top and within the glacier right there. And that formed what's called glacial till, which is just a big mixture of different types of soils but generally quite competent soils, and again, desirable soils for supportive wind turbine foundations. So we've got good soils in the Des Moines lobe there, but what we don't have is we don't have the presence of things like hills. You know, when you're in southwest Minnesota, it's nothing but open fields and a lot of wind blowing, but the wind is it's blowing most predominantly at the tops of hills. So you have other things that you want to look at in terms of the geologic history. Glaciers form what's called moraines, and moraines are basically big piles of debris along the sides of the glacier. Those are called lateral moraines, and then also moraines at the end of the glacier, which is called a terminal moraine. But basically, you can imagine a glacier is just moving along and piling up all the soil around the perimeter of the glacier. Why that's important is if you go to southwest Minnesota now, you see these ridges. They're subtle, but there are ridges there that are as much as 100, 200 feet above the surrounding area. And that's important to wind power developers because just an extra 100 or 200 feet in elevation is a big boost in terms of the consistency of the wind that blows in that area. So wind power developers are specifically looking at those areas for wind power development. It's not quite a geotechnical engineering aspect, but what plays into that is, again, it's a glacially deposited soil, so it's typically a soil that's been there for a while. It's been compressed by the weight of the glacier. And again, it's typically a strong soil, very low compressibility soil, and it's a desirable soil to found a wind turbine on. So I won't talk much more, but I will say this. If you've been to southwest Minnesota, if you had this map in hand, you could pretty much follow where most of the wind turbines are in southwest Minnesota. They follow that northwest, southeast trending ridge right there between the Coteau de Prairies and the Des Moines lobe there. There's also a fair number of wind turbines directly south of the Twin Cities near the Albert Lea and Austin area. It's not quite as predominant there, but there's again another glacial moraine. So it's just a subtle increase in the relief in the land there that leads to a very desirable wind situation for wind power developers. Other aspects of the geology that we're concerned with for geotechnical engineering is specific risks or hazards associated with a site, and we're looking at which sites or which hazards are present at a site. If any of those hazards are fatal flaws, we're looking at how we can mitigate or reduce the risk associated with those hazards. There can be a number of different geologic hazards present at sites, and each site is typically going to be unique for what types of hazards are present. So looking in the figures here, the picture on the left, it shows a hill. So we've got a generally desirable situation for a wind power developer. They're going to want to put their turbine on top of that hill. But as you can see there, there's a slope failure where the soil near the surface along the edge of that hill has slumped and slid down into the valley there. So we want to be aware of things like the potential for slope failures, and we want to avoid or recommend to our clients to avoid locating wind turbines near the edges of these slopes to prevent catastrophic failure of the wind turbine. In the picture on the right, there's a number of different geologic hazards. We've got a wind turbine sitting on a profile, a generalized profile anyways, of a layer of sand over a layer of clay, and then at the bottom there's a big unit of limestone bedrock. As you can see, the wind turbine is correctly located a good distance away from the edge of the hill here. It's shown as a cliff there, either a cliff or a steep slope. Again, we've got a situation where we have a potential for a landslide, and obviously we want to avoid siting wind turbines in those areas. Also shown on the right of that picture is a fault. You don't think of faults here in Minnesota, but when you're doing projects in California, there's faults running all over the state of California, and you obviously want to make sure that you've researched where all the geologic faults are running through project sites and working with your clients to make sure that they're not constructing wind turbines directly on top of a fault, as that could spell disaster in the event of an earthquake. Also shown in this picture in the bottom in that limestone formation is the presence of either a mine or of a cave. Those kinds of things can be okay in certain situations, but in some cases you may have situations where the roof of that mine or the roof of that cave starts to collapse in on itself. And basically you get the roof collapse in on itself as it's shown in this picture, and then the roof above that, after a few years of weathering, collapses down, and you get this retrogressive failure where all the rock starts to collapse in on itself, and it creates these voids. Once all the rock has collapsed and it reaches that boundary with the soil doesn't have nearly as much strength as the rock does. So the soil, through erosion, through water moving through the soil, it starts to just get deposited in these voids, and you ultimately get to a situation where this void, which is way down below the ground surface in a mine shaft or in a cave, has progressed all the way to the ground surface, and you have a situation where the wind turbine can sink as much as 5 or 10 feet. And we've been at project sites out east where you're walking around along a ridgetop and there's just big holes in the ground as a result of these voids that are out there. So we're looking at things like that, and I'm working with our clients to make sure that they're not building their wind turbines right on top of these hazards. So beyond looking at the geology, we want to look at the composition, the different types of soils at a site. So we're looking at what type of rock, again, what type of soil is present. But beyond that, we're looking at what the breakdown is for these materials. So I won't bore you too much with this, but soils are broken up into 3 different components: sand, clay, silt. Those basically just represent different sized particles that comprise the soil itself. So we're doing, we want to understand how much of each component we have, because sand is going to behave differently than a clay will, and we need to take that into account in our geotechnical evaluation of a wind project site. Similarly, in terms of a soil composition, if you look in the bottom of the slide here, we've got a generalized schematic close-up of what soil looks like. You can see all the individual soil particles, with water sitting in part of that soil and then air sitting in the spaces between the soil particles. That can be broken down into what's called a 3-phase diagram, where in that specific unit of soil we can represent how much of that volume is occupied by the soil itself, or the solid phase, how much is occupied by water, and how much is occupied by air, which doesn't seem important until you look at things like compressibility of the soil. Compression of a soil happens when you apply a load to a soil like that, and what happens is those different particles want to reorganize themselves into a denser manner, which forces out air, which easily comes out of soil, but it also forces out water out of soil, and ultimately leads to settlement of that soil supporting a wind turbine foundation. So we're looking at these things, we're looking at the different compositional makeup of soils, because that's going to tell us how much soil is going to compress or settle below a wind turbine foundation. It's also going to tell us how quickly that settlement is going to occur. We're also looking at the strength characteristics of the soil. The soil has to be strong enough to support the heavy loads applied to it from a wind turbine foundation. And then lastly, we're looking at the elastic properties of the soil, and specifically how stiff a soil is. A wind turbine foundation is a dynamic machine that's constantly moving and rocking back and forth, loading and unloading, as Jennifer mentioned. And that creates a dynamic load, and it has the wind turbine system itself has a natural frequency. And we need to look at how stiff the soil is and how the frequency of that soil compares to the natural frequency of the wind turbine system, and hopefully avoid things like resonancy that can lead to problems in the performance of a wind turbine. So how do we get this information? Well, we have to go out to these project sites and collect samples and test the soil and rock at the site. So there's a variety of different ways that we can do our geotechnical field investigations. We can go out and do test pits, basically an engineer or geologist at a project site with a backhoe, digging holes, say 10 to 15 feet in the ground. It gives us an idea of what the soil profile looks like. If there's bedrock, say 10 to 15 feet below the ground surface, we can figure out exactly at what depth that rock is located and what the rock surface looks like. We're also doing soil borings. Soil borings are basically like drilling holes, deep holes into the ground, and conducting tests and collecting samples of the soil as we drill these holes in the ground. And that helps us understand what the soil layering looks like below the ground surface, and also an estimate of how strong the soils are and how much they may compress. So we're collecting soil samples as we do these soil borings or perform these soil borings. So typically we're doing split spoon sampling and Shelby tube sampling for soil sample collection. If we do have sites where there's rock present, we are coring into the rock because we need to figure out how competent the rock is itself. We may hit a void. We'll usually see that in the core samples, and voids are important, as I mentioned on one of the previous slides, because we want to avoid situations where caves could potentially collapse immediately below a wind turbine. In this picture, it's a drill rig basically. That's what we use to drill down below the ground surface and collect soil samples. The depth that we typically drill these holes is generally related to the depth of the foundation influence, which is typically on the order of 1 to 2 times the width of the foundation itself. So as I mentioned previously, a foundation is typically 50 to as much as on the high end 70 feet in diameter. So we're drilling holes or testing at every single turbine location and going down to a depth of 50 to 70 feet below the ground surface. We also do other types of field investigations called in situ testing. In situ testing is essentially doing a test of the soil in place in the ground right there, but we don't get to collect any samples. The most common method of in situ testing is what's called cone penetration testing, or CPT. And it's basically taking a big truck here that weighs about 25 tons and pushing a 1.5 inch aluminum rod with a conical tip on it that's instrumented into the ground at a specific rate, and measuring the resistance of the soil and some other properties as we push it into the ground. So looking at the close-up of this conical tip, we've got the tip itself that's attached to a pressure or a load cell. Above the tip, there's a frictional sleeve that surrounds the rod. And that sleeve is there to measure how much friction is developed by the soil sliding along this rod as it's pushed in the ground. And in between those two, we have a saturated porous filter, which allows us to measure the presence of groundwater and also how much pressure is in the water below the ground surface. So using that all that information together, we can develop a profile of the soil, which helps us understand what the soil layering or the soil stratigraphy is like. That's that squiggly line that runs down below that schematic of the CPT truck. So you can see your differences in your various layers. And we can also use this information to estimate things like soil strength and soil compressibility factors, which will play into our geotechnical analysis that will follow. So after the field investigation phase, we take our samples that we collected with our drill rig or with our test pits, and we do a series of laboratory tests to better understand the properties of the soil. We're doing physical tests, typically moisture content or Atterberg limits, sieve hydrometer, grain size analysis curves. We're looking at what the in situ density is of a soil, just to better understand the physical properties of the soil itself. But beyond that, we need to do laboratory testing to specifically assess how strong a soil is, because that's directly related to how the ability of a soil to support a foundation and prevent the actual soil below the foundation from failing. So we're doing strength tests. A common strength test in the laboratory is a UU triaxial compressive strength test, which is shown in the diagram here. The soil sample is placed into a cell, and the cell is filled with water, and then a uniform pressure is applied around the sample itself. And then the sample is loaded axially until a point at which it fails. And from that test result, we can then figure out what the undrained shear strength of the cohesion of the soil is, which directly plays into our bearing capacity analysis. We're doing other laboratory tests to evaluate the compressibility of soils. So consolidation testing is a common test that we would do on saturated clay samples. And that's going to tell us how much a clay is going to settle under a specified load, which again is going to be important in our geotechnical evaluation or our analysis that we follow this with. Beyond that, we're also doing standard Proctor tests to evaluate the density of the soil as it's recompacted. So for a wind turbine foundation, typically a large hole is dug into the ground, the foundation is constructed, and then the soil that was removed from that hole is used as backfill material over the foundation to bring the earth back to grade there. We need to understand, or the foundation designer needs to understand the density of that soil, because that plays directly into their calculation for the factor of safety for the overturning moment, as Jennifer touched on earlier. Beyond that, there's a few special laboratory tests for looking at providing recommendations for the civil engineer and the design of the road sections, how much gravel they need to place at a given site to construct a road to gain access to these turbines. We're doing California bearing ratio tests. We're also performing thermal conductivity tests to evaluate the thermal properties of a soil. So for each wind turbine, it's generating power. That power is transferred down through a cable, a fairly large cable that's buried underneath the ground surface, and that cable then is routed to a collector substation, and that substation ultimately transmits the power to the main electrical grid. Well, this cable, it's carrying quite a bit of power, and all that power moving through that cable makes it get pretty hot. And so we need to understand, or the electrical engineer needs to understand the thermal properties of the soil to make sure that they're adequately designing the cable and any backfill material around that cable to resist the heat generated from the electricity moving through that cable. Beyond that, we're looking at general characteristics of a site and looking at the laboratory and field test results to evaluate what type of foundation system is most suitable at a site. At sites where there's soil conditions, and they're generally good soil conditions, so high strength, low compressibility, a spread footing foundation is a typical foundation that's used, and that's probably the most common foundation system used here in the United States. If a given site has generally poor soil conditions, so weak soils, very compressible soils, we're looking at other types of foundation systems, such as a pile foundation, where we're essentially taking big steel pipes and pounding them into the ground, say a depth of 100 feet below the ground surface, to take the load from the wind turbine and transfer that load down to a fairly substantial depth where we reach better soils that can take on the load from the wind turbine foundation. At sites where there's rock present, depending on the characteristics of that rock, how strong it is, we may looking at our evaluation of a rock socket or rock anchor design where the foundation is directly poured or attached to the rock itself, so we're utilizing a lot of the strength of the rock. It's important because the rock socket or rock anchor foundations typically use quite a bit less concrete and steel than a typical spread footing foundation design is using. So our clients like it from an economical standpoint because it saves them quite a bit of money in terms of this foundation design. And when you're looking at projects where there's 100 wind turbines in each foundation, say costs $200,000, and we can cut that cost in half, it's a fairly substantial savings, and our clients are typically looking at wanting to pursue options like that. On the flip side, there can be other factors like project schedules. A lot of these projects move really fast, and designing a rock anchor or rock socket foundation takes quite a bit longer than a typical spread footing foundation design. So if the project schedule doesn't allow for adequate design of a rock socket or rock anchor foundation, sometimes we're instead designing spread footing foundations at sites just to keep a project on schedule, because that's more important economically to our clients and the savings in the reduction in materials. And then beyond that, we're looking at factors like construction risk. A lot of wind turbine design build contractors have built all sorts of spread footing foundations, and they're very comfortable building those types of foundation systems. However, when you look at things like pile foundations or rock socket, rock anchor foundations, those are not unique foundation, or those are atypical foundation systems. And we have to look at how much risk is associated on the construction site, and more importantly, the contractor has to look at that and make sure that they're comfortable and they can effectively build those foundations for a client. So taking all that information in, we then have to do a geotechnical analysis of our project site and evaluate a number of different factors, 3 primary factors, bearing capacity, settlement, and stiffness, to be able to make recommendations for the foundation engineer to use in their foundation design. So the first one we're looking at is bearing capacity, and that's essentially the ability of the soil to carry the load of a wind turbine foundation. And it's literally the point where the soil reaches an ultimate, what's called an ultimate bearing capacity, where if there's any more load applied to it beyond that ultimate bearing capacity, the soil will literally fail and shear, where it will move, it will just displace downward and then outward. So you'll have soil moving, the foundation will move down, and then you'll have these big piles of soil surrounding your foundation. And that's obviously an undesirable situation. So in order to do our bearing capacity analysis, as I touched on previously, we need to know the strength properties of our soil or our rock at our site. And using these properties coupled with loads from a wind turbine, we can properly assess the bearing capacity or the carrying ability of these soils. The loads from a wind turbine are very eccentric. As Jennifer touched on, you've got that pretty high overturning moment. So on one side of the foundation, you may have almost no load applied from that foundation to the ground, but on the other side of the foundation, you have a fairly substantial load. In terms of our geotechnical analysis, we take this eccentric load, and using empirical formulas, we can break that down into a uniform bearing pressure applied to a soil system. And then using theoretical formulas, we can calculate what the ultimate bearing capacity of the system is and make that recommendation to the foundation designer to use for their foundation design. One thing I think it's important to note is that in this phase of the process, the geotechnical engineer is working in direct contact with the foundation designer themselves, just to make sure that they're getting the information in terms of the dimensions of the foundation, the loads being applied, so that the geotechnical analysis is being properly performed. The second set of analyses we do on the geotechnical side is evaluate settlement. Wind turbine manufacturers have specific limitations on how much settlement can occur in the wind turbine. And more importantly, they're looking at, as you can see on the third bullet point there, how much differential settlement can occur. And that's basically differential movement across the tower foundation itself, which can lead to a situation where the foundation is tilting, which tilts the entire wind turbine. And if a tower is tilting too far, it creates additional loads on the foundation, but more importantly, it creates additional loads to the mechanical elements within the wind turbine itself, and can lead to a premature deterioration of the turbine and the life of the turbine itself. So settlement is essentially permanent deformation of the soil immediately below that wind turbine foundation under the load from the wind turbine foundation. So it's a reduction in that volume of air and water in that 3-phase diagram that I talked about earlier. When we're looking at settlement, we want to understand what the load history of a soil was. As I talked about when I talked about geology, geology is important when we have glacially deposited soils. Those soils have typically seen the weight of very heavy glaciers on top of them. Those soils are desirable because they've already been compressed from the weight of the glaciers. So putting a wind turbine that has a load much less than what a glacier weighed 12,000 years ago is in that type of situation where you have glacial soils. It's a desirable situation because you have soil that's not going to deform very much, so we can minimize our settlement and usually control that differential settlement to a value that's acceptable to the wind turbine manufacturer. We're looking at how those soils were deposited. As I touched on earlier, some soils are deposited by glaciers, but others are deposited by wind and water. Soils that are deposited by wind and water are generally deposited in a loose state. Soils that are in a loose state generally exhibit quite a bit of settlement. So we want to understand that and find ways to deal with that if we need to, which I'll touch on a little bit here. I talked about earlier soil compression or settlement, it can be a long or a short process. Sands, for example, will settle immediately. So you apply the wind turbine or you build the wind turbine and get it fired up, it's going to settle right away. Soils like clays are very low permeability soils, so they don't allow water to move through the soils very easily. And when you apply the load of a wind turbine foundation, it wants to force that water out, but because the permeability is so low, it takes a really long time for the water to move out of those soils. So while soils like sands settle almost immediately, clay soils may take 5 years to settle. So if you don't adequately look at the settlement potential of a site with clay, on day one, you may not have any settlement issues, but 5 years later, you may have a turbine that's sinking into the ground. And obviously, we want to avoid that type of situation. So we're doing our settlement calculations, again, using theoretical and empirical formulas. The last primary geotechnical analysis or component of geotechnical analysis we're looking at is soil stiffness. And why that's important is the wind turbine, it's a dynamic machine, so it's creating this rocking of this foundation at the micro level. It's loading and then unloading, so it's moving back and forth. It's a dynamic load applied to the soil. And we need to understand how stiff the soil is itself, because we want to make sure that we don't have resonancy with the foundation system and the soil that's supporting it. We want to make sure that our soil is substantially stiff, such that its natural frequency is substantially different from the resonant frequency of the wind turbine system. If we don't protect for that, improper soil stiffness can lead to resonancy, which leads to substantial oscillations within the wind turbine. That leads to quite a bit of vibration within the tower, which can affect the power output from a wind turbine, and long-term can affect the life of a wind turbine, the tower, as well as the foundation when we look at things like fatigue. It goes without saying, but rock's very stiff, so generally not an issue in terms of stiffness. We don't really worry too much about that, but when we're dealing with soils, they're very flexible in terms of their stiffness, so we need to be very careful and assess how stiff the soils are and make sure that we're adequately protecting against stiffness issues with the foundation designer. A couple other things that we look at in our geotechnical analysis. Some soils are very corrosive. For example, if you have a lot of sulfate in the soil, you have concerns that sulfate, if it gets dissolved by water moving through that soil, could potentially penetrate your foundation, attack and eat away at that concrete, and over an extended period of time deteriorate your foundation to the extent that it can be quite severe and effectively reduce the volume of your foundation. If you've got a smaller foundation than what you started with, your loads apply to the soil change, and the performance of that foundation is affected substantially. So we're looking at how much sulfates or chlorine is in a soil. We're looking at the pH levels of the soil, and then working with the foundation designer to make sure that they specify certain types of cement that are resistant to sulfate. They can specify a lower water to cement ratio in their foundations to make a lower permeable foundation, and then they could also, in some extreme cases, specify surface seals to prevent any of that sulfate from ever entering into the foundation. So at some of our sites, we have soils that are weak soils, but they're not to the extent where we need pile foundations. Pile foundations are very expensive foundation systems, and clients tend to want to shy away from those types of foundations. So we have, sites where there's, for example, wind-blown soils or loess. Loess is a type of soil that's commonly found in the central part of the U.S. It's essentially silt that came out of big rivers coming off the Rocky Mountains during the last ice age. That were deposited in the river basins there. As the winds blew across the Rocky Mountains, it picked up those silt particles, carried them as much as 500 to 1,000 miles, and deposited them in places like the state of Iowa. In some cases in Iowa, you may have 50 to 60 feet of this loess there. Why that's important from a geotechnical standpoint is because it's a wind-deposited soil. It's deposited in a very loose manner. That it can be somewhat cemented. It can hold up to loads initially, but If you build a wind turbine foundation on these types of soils and then introduce some water into the system, the soils can exhibit what's known as sudden collapse, where the soil can settle as much as 2 to 3 feet in a matter of a very short period of time, less than a day. And obviously having a turbine sinking into the ground is an undesirable situation. Other sites with poor soil conditions include sites where there's uncontrolled fill or previously placed fill material, and then just generally weak soils. So we're looking at ways to mitigate this collapse phenomena in the loess, keep our settlement to a tolerable level, and increase the strength of the soil to make sure that we're properly designing it for bearing capacity. So the easiest solution to deal with problematic soils at a site is just to remove and replace. So we're digging out these soils and replacing with specific types of soils that can be compacted, and those soils generally have very high strength and have low compressibility. So it's a desirable situation to use those types of soils. The problem is if the undesirable soils are of fairly substantial thickness, nobody wants to dig a hole 40 feet deep in the ground that's, say, 120 feet in diameter. It's just much too large and it gets very expensive. So we're looking at other options. And a couple of those options include dynamic compaction as well as the use of stone columns. This photo is dynamic compaction. It's pretty crazy. Here's a site where the intent is to build a wind turbine foundation right where this picture is taken. But here, this is at a site, I believe, in eastern Oregon. And in eastern Oregon, there is quite a bit of this wind-blown silt or this loess. And here, I think there was probably on the order of 30 to 40 feet of this material. So it's too much material to dig out and replace with engineered fill. So we're looking at options like dynamic compaction. And what dynamic compaction is taking a big crane, lifting up a big steel plate that weighs on the order of 30 to 40 tons, lifting it up 50 to 60 feet in the air and then letting go of it and let it fall and hit the soil and create these massive craters here. So you can kind of see the craters in the picture there. They're about 6 feet in diameter and like 6 feet deep. Literally, you drop this weight and it's like it just disappears into the soil. So this crane does it on a grid pattern, as you can see here. The contractor comes in after they've done one layer of this dynamic compaction, comes in with a dozer, pushes all the soil around, relevels it. The crane comes back in and drops the weight again, but at an offset grid to kind of cover up those gaps that they've left in between the craters here. So what they're essentially doing is forcing the soil to collapse or compress the soil so that we don't have those collapsibility or settlement issues during the life of the turbine. As I mentioned, another option is the use of stone columns or geopiers. In the picture on the right, it's an excavation for a wind turbine foundation. You can see the tops of these stone columns. Stone columns, as shown in the picture on the left, are essentially drilling holes about 30 inches in diameter through your weak soils, and then taking rock and ramming the rock down the hole and compacting it into very tight lifts. So you have these columns of stone within your weak soil unit, and the columns of stone serve as the stone is compacted in the soil. Those columns of stone serve to densify the weak soils surrounding those columns and generally create a composite soil mixture that has very low compressibility, high strength characteristics. Again, that's what we're looking for our geotechnical properties of our soil to support a wind turbine foundation. I'm almost done. Last slide. Last thing the geotechnical engineer needs to do is prepare a geotechnical report, kind of summarizing everything that we looked at. There's different types of geotechnical reports depending on what phase a project is in. If a developer is just looking at the feasibility of a project, they're not yet ready to build it, but they just want to look at what types of risks or hazards may be present at a site. We're completing desktop studies to evaluate those hazards and address them and educate the developer on that. If a project has moved beyond the feasibility stage and a client is looking to try to get a good handle on what a typical foundation design might look like so they can price out how much a project would cost to build, We're going in and doing a limited program of geotechnical evaluation and preparing preliminary geotechnical reports. And then once a project is ready to go full design and then build, we're doing a full geotechnical evaluation where we're evaluating every single turbine location and then preparing a complete geotechnical report to be used in the actual design of the foundation and construction at the project site. A couple other odds and ends reports that we also do on the geotechnical side are electrical resistivity reports to help electrical engineers as they design the grounding grids for wind turbine foundations. Turbine foundations, wind turbines are 300 to 400 feet tall, even 500 feet tall if you look at the tip of the blade. So they're big lightning rods and they get hit by lightning all the time, and the electrical engineer needs to design proper grounding systems to take that electricity from the lightning and dissipate it into the ground. As I mentioned earlier, we're also including recommendations for road section designs based on the results of California bearing ratio tests, and then also providing results of thermal resistivity testing to assist the electrical engineer in the thermal design of cables carrying the power from the turbines to the substations.
So Rob spent a lot of time talking about the geotechnical side of things. You can tell that's really important for us, to get a sense of what kind of soils are we dealing with. Once that part is all done, then we get into the foundation design. So I can't really do much of anything until his work is done. So first off, just wanted to give you an idea of the foundation types. Rob talked about some of them, but I have some pictures here to show you. First, talking about tower types. So we do have, I guess, three main kinds of towers. There are lattice towers. These are ones that you might see for some of the smaller turbines out there, or some of the ones that were designed maybe in the early 90s. The most common tower is the steel tubular tower, though. That's what we'll see all over southwest Minnesota, Iowa, all across the country for land-based towers. A new tower that's, I guess, more innovative is a cast post-tension concrete tower. This photo is actually in Spain. It's something that there's only been a couple that have actually been put up, I believe, in the world. But it's getting a lot more interest from developers just because it is something that allows turbines to be taller. It is more difficult for construction now, so it's something that's a little bit new, and people are just kind of testing it out at this point. So we have the tower, and then we need to connect it to our foundations. So there's a couple different types of connections. The most common is an anchor bolt embedment plate connection, or I should say the most common in the U.S. And so this is basically, we have anchor bolts that connect to the base of the tower, and they run into the turbine foundation and are connected to an embedment plate, a steel embedment plate at the base of it. So all you see there at the top in the photo, once the foundation is all built, are the tops of those anchor bolts. Oops. Oh, what did I do? Sorry. Okay, thank you. All right, sorry about that. Another type of connection is what's called a foundation mounting part, FMP. It's basically an extension of the tower that goes directly into the foundation. This is more common in Europe for some reason. They like this type of connection. But it also makes it a little bit more complicated for doing the foundation design. We have a top mat of reinforcing steel that needs to be placed, and we have this big piece of steel in the way. So it gets kind of tricky. There's different holes that go into the section there in the foundation that we're trying to run our steel through. So just a little bit more complicated, but it just depends on the type of turbine and where something's being built. So the most common type of footing is a spread footing, as Rob mentioned. I should say the most common for land-based foundations. So this is a photo here. You can see that, again, that anchor bolt cage. Then what's shown here is the workers standing on the top mat of reinforcing steel, and then there's another layer bottom reinforcing steel in that. So they're just pouring the concrete here. Another type of foundation is a P&H patented foundation. This is something that was developed by Patrick and Hendrickson. So that's the P&H there. But basically what this is an embedded steel can. So they excavate the soil, set in these 2 layers of steel. Then that gets filled with reinforcing steel and concrete. And then they're filling it in the inside of the caisson there with the backfilled soil. So the excavated soil they put back in there, and then they also compact it around the exterior of the cans there. Something that's a little bit tricky is this does rely heavily on skin friction of the soil, so it can't be placed in all types of soil conditions. And if it is placed in those soil conditions where it's not best suited, there can be some movement of the foundation, which is obviously not a good thing. Another type of foundation is a pile foundation. As Rob mentioned, we want to do basically everything else that we can before we get to this. They are very, very expensive, and also a lot of labor goes into constructing these foundations. So basically what this consists of, well, what you're looking at here is a pile cap. You see the tops of the piles sticking out from the concrete there. It's just a thin mud mat of concrete that the piles are sticking out from. But if there are poor soils and if we can't do some other sort of mitigation like stone columns or dynamic compaction, then we need to go to a pile foundation. So we run these piles all the way down to a competent soil or bedrock layer. We might embed it into the bedrock there to make sure that we're getting enough stiffness in the piles. And then we connect it to the turbine, to the tower there, with a concrete pile cap, which you can see has a lot of reinforcing steel there. And then again, the anchor bolt cage. Another type of foundation is a rock socket foundation. So this is where we're dealing with rock conditions. So it might be more economical in a situation where we have really shallow, strong rock to do this type of foundation instead of a shallow spread footing foundation. So what we do here is we blast, it's generally a 20 by 20 by 20 footprint into the rock, and basically set this steel can and fill it with reinforcing steel and concrete, and again that anchor bolt connection. So this basically ends up being a large concrete extension of the tower into the rock. So we're really utilizing the strength of the rock in this situation, and this is something that is definitely can save a lot of money just due to the reduced size in comparison to a spread footing foundation. Another type of foundation is a rock anchor foundation. Again, this is where we have strong, shallow bedrock that we would use something like this. In this type of foundation, we have steel tendons, anchors that we embed into the rock. And so we're, again, relying on the strength of the rock there. And we tension those anchors, and then we tie it again with a anchor bolt cage, and then a concrete cap there with reinforcing steel, again, to tie that into the tower. Again, this is much smaller than a spread footing foundation, so again, we can save a lot on cost there and have a lot less excavation of that rock, which can get quite pricey as well. So getting into actual foundation engineering here, we've took a long time. There's a lot that happens before we can actually get to the design. So I'm going to just walk us through kind of a basics, really high level of a typical spread footing foundation. So as we said, there's a lot that goes into it. So first off, we need the loads. As I mentioned, those do come from the turbine manufacturer. So taking a look at the extreme loads, the normal operating loads, and fatigue loads that we discussed earlier. Also in the turbine load document that we get from the manufacturer is the tower flange dimensions. So that is something that's set. We can't change that. So we get to the dimensions of that base flange at the bottom of the tower. We have the size of the holes that are going around that base flange where we need to connect our anchor bolts to then connect it to our foundation. So something that we're limited on, which can get kind of tricky in some instances. We also have serviceability requirements. So Rob talked about the stiffness and the settlement. We need to take a look at those parameters. Turbine manufacturers have limitations on what those need to be. We also take a look at the materials. So, we might have a project in Hawaii say that concrete is very expensive there, but steel might be a little bit cheaper in comparison. So we might want to take that into account when we're doing our design instead of just giving them something that we would normally do in another part of the United States. And then we have our geotechnical parameters. So Rob talked all about that, and basically we get that geotechnical engineering report, work together with the geotechnical engineer to make sure that we're interpreting that correctly, and then use that in our design. So first off, we take a look at the stability, overall stability of the foundation, and this is really where we get kind of the first cut at sizing the foundation. So we take a look at overturning and sliding. So overturning is, again, that overturning moment wants to push the tower over and the foundation. So we need to make sure that we have enough weight to resist that. So we might take a look at making the foundation wider, might make it deeper, adding the weight of the concrete as well as the soil to resist that overturning. We also take a look at sliding. So what's that translational movement of the foundation? This tends to be a pretty massive piece of concrete, so that doesn't typically control for our foundation design, but we still need to check it. So after we get through that, we take a look at bearing capacity. So again, this might affect the width of the foundation. Typically, we get those parameters from the geotechnical engineering report that they'll take a look at what our bearing capacity is under the extreme and normal operating loads. And once we've sized our foundation, we need to make sure that we're meeting those criteria. If we don't, we might take a look at doing some sort of soil improvement or soil mitigation versus making the foundation larger, just depending on the cost of a certain situation, especially if it is isolated to certain turbine sites versus the entire site, for example. So again, this depends on what kind of properties we have of the soil. So if you're sitting on rock, it's really good. If you're on a compressible soil like a less, we might have to work around that. We also have to take a look at the contact length. So when that turbine sees an extreme load, when it's in operation, how much of the foundation, the bottom of the foundation, is in contact with the soil under those loads. So it's not always 100% in contact with the soil, which might be a little bit surprising, but there's guidelines that Germanischer-Lloyd, GL, puts out that says that under our normal operating load, so what the turbine is most often seeing, that we do need to be 100% in contact with the soil, but under an extreme load, we can actually reduce that to 50% in bearing under that load. So Rob talked about the stiffness of the soil. As I said, the turbine manufacturer gives us parameters to make sure that we're meeting those requirements. We need to make sure that we meet those requirements because that goes into their design. There's that natural frequency of the tower, so we don't want to have that resonance with the frequency of the tower. So something that typically does not control a foundation design unless we have really poor soils, but it is, again, something that we definitely need to check. Excuse me. Take a looking at differential settlement. I've talked a little bit about this as well. Again, this is given to us by the turbine manufacturer, that it's really a differential settlement that we're most concerned with versus an overall settlement. And that's, again, to make sure that we're not having a crooked turbine and tower, like the leaning tower of Pisa here that we have shown. So typical limitations on the differential settlement is about 0.71 degrees. So that's for over the loaded area of the foundation. So that's under that extreme event that we would take a look at that, or it comes out to be about 3 millimeters per meter across the foundation. So getting into the actual design, more the structural side of things, first taking a look at the connections. So we have the base of the tower, the turbine, base flange that gets connected to our foundation. So as I said, the most common type is an anchor bolt connection, an anchor bolt cage. So we need to take a look at the different modes of failure that we could potentially have here. So first off, we have the anchor bolts that get connected to that base flange. There's a bit of a buffer between the base of the turbine and the top of the foundation, so we put grout in there to make sure that we have a level surface. So we need to design that grout. So we design it for bearing of the grout, so we determine what that strength needs to be so that it doesn't crush under the load. As I said, we are limited on the size of that base flange, and so we might have some difficulties if it's a really small area but a really high load. So our strengths can get up to up to 20,000 psi for that strength in comparison to the concrete strength, which might be more around 5,000 psi. So really high loads that the grout sees, and we need to make sure that that doesn't crush under that load. From the grout there, that load gets transferred to the top of the concrete and the pedestal. So again, we want to make sure that it doesn't crush, crack, split the concrete. So we make sure that we have adequate strength. As I said, typical concrete strength for wind turbine foundations is 5,000 psi. So if we can, we want to keep it at that 5,000 psi. It gets very expensive if we have to go to a higher strength concrete. So we might get a little bit creative. We might try to expand the width of the grout to spread out that load a little bit more, make the pedestal wider. Again, that kind of, there's a bulb of stress that gets created, and that kind of gives us a little bit more room to work with. So there's a couple different things that we can do there. Then we have the anchor bolts themselves. We need to design, determine the size as well as the strength of those bolts. There's just a few types of bolts that are typically used for wind turbine foundations. So we do have some limitations there. Again, we are limited on that tower base flange as far as the holes that we have to work with. So again, it can get a bit tricky there trying to make sure that we have adequate strength for what we're given. And then at the bottom of those anchor bolts, we have a steel embedment plate. So that really ties that whole connection into the foundation. So we need to design that embedment plate as well. That's something that, really just looking at the thickness of the plate, we use the same dimensions as the tower base flange just for ease of construction, but need to take a look at, the stresses, the tensile stresses in that steel plate. One of the other things we take a look at is pull out of that entire connection as well. So I guess not really shown here, but we typically provide, we call them Z-bars, but it's just a reinforcing steel that goes on either side of those anchor bolts. Typically we match the number of reinforcing bars to the number of anchor bolts there. So that's really designed, those steel reinforcing bars are designed to take that tensile force that's created from the pull-out force from the turbine. So getting into the actual reinforced concrete design, so of the footing itself, what we use is load and resistance factor design. I'm not sure how many civil engineers are out there, but you might have heard of that. All right, we got a couple. So load and resistance factor design takes a look at applying load factors as well as material resistance factors to account for any variability. So a load factor might be applied to the wind load because, yeah, it's supposed to see this certain wind load, but it might get exceeded at some point. So it just gives us that extra buffer that we need in our design. We also have material resistance factors. So say for the concrete, it's a 5,000 PSI concrete, but there's some variability in there. And so that's to make sure that we have enough room there in our design. So that's the basis of what we're doing in our design. So what we first start off doing is calculating the soil bearing pressure. So we have that overturning moment. It creates a pressure on the soil, and that's really trying to push up the bottom of the foundation. So again, for civil engineers, concrete is really good in compression, but it's bad in tension. So we have steel reinforcing mats that we design for those internal moments that are created in the foundation. They're designed for those tensile forces that are created. We also have to take a look at one-way and two-way shear. So basically the edges of the footing splitting off underneath that load that's from that pressure from the soil. So that typically would control our thickness of the foundation. Typically the one-way shear controls that. Another thing that we take a look at is two-way shear. So that's really a punching shear of the whole pedestal going through the foundation, basically. So we need to take a look at that, and so that really determines thickness of the foundation. We'd already determined the width from more of the stability characteristics that we take a look at, and then taking a look at designing the steel reinforcing mats for those moments. Then we take a look at fatigue. This is something that is a bit tricky. There is not a great code out there for concrete and fatigue. So we've taken a look at some different codes out there and tried to come up with a way of dealing with this. But we, again, need to take a look at the concrete and the reinforcing steel under those fatigue loads. So failure under fatigue is really more of a progressive failure. So over the life of the foundation under that cyclic loading, are we going to have a failure there? So we need to take a look at those as well. Rob mentioned this, the electrical engineering side of things. A couple different things that our electrical engineers take a look at is a conduit layout design. So we have all of the power cables coming from the tower that need to go out to the transformer. So that goes actually through our foundation. So an electrical engineer needs to take a look at designing the conduit layout for those cables. And then we also have the ground grid design. So again, it's like a big lightning rod, and so we need to make sure that we're not going to have any harm of workers or of the electrical components of the foundation. So once we get all done with the design, we prepare a design report. So it's all of our calculations that we do. Our reports are quite extensive, actually. There's a lot of different calculations that go into this. I'm really doing this high level, so not getting into the nitty-gritty, but we have the design computations. Those might get reviewed by third-party reviewers, so we definitely need to be thorough in our design. And then we have the design drawings. This is just an example shown here of what kind of a typical drawing looks like, but these need to be constructed, so the contractor needs to know all of the dimensions, sizes of the reinforcing steel, spacing, all of those details, as well as the technical specifications, so the material strengths, all of the testing that's involved. We have geotechnical testing that we require, so taking a look at the backfill soils over the foundation, that's really critical to make sure that we have enough resistance to overturning. So we make sure that we're doing enough tests there and getting the appropriate soil weights over the foundation. We do testing of the materials themselves, so we take concrete cylinders and break those, making sure that we're meeting our requirements. We can get into some interesting cases when they don't make strength. There's some different things that can be done there, but it can get quite complicated. So part of the documentation there is getting all of those submittals and all of those reports from the contractor as it's being built to make sure that it does get built properly. So I just wanted to highlight a little bit on the research that we're doing out at the Umore Park Foundation. I don't know if any of you have gone down to Rosemount, Highway 52. You can see it right from the road. It's pretty cool. I drive past there on the way to my parents all the time, so I like to see my turbine. But we were involved with the engineering of that, so the foundation design, geotechnical engineering, civil site design, everything on that. But we're also doing some research on that. So the reason why we're doing research is because really hasn't been done before. These are very, very large structures. The design codes out there don't tell you how to design a wind turbine foundation. They're building codes. So we end up pulling our design equations from several different codes, papers out there. So we're trying to do some research to see, are we really designing these appropriately? Are we seeing the loads that we expect to see? Are we seeing the settlement that we expect to see? So just getting into that, we are still working with the University of Minnesota on doing that research. So don't have any set results yet, but hopefully we'll be getting some interesting results then and likely be doing some presentations or writing a paper on that. Just wanted to highlight some of the construction here for you. So I have some nice photos kind of walking us through how this actually gets built. So first off, we have site preparation. So this can be really easy or really hard. In Southwest Minnesota, for example, and farmland, it's pretty easy. There's typically roads in the farms already. We might have to make those roads a little bit stronger to make sure that it can carry the loads during construction and when they're bringing the turbine components out to the site. Otherwise, we might have a site that's in the mountains and we need to design those roads and, first of all, get equipment out there to do a geotechnical investigation and then, for the construction piece of it as well. So there can be quite a lot of work that needs to happen before we can even get construction going. So first off, we do the excavation. So generally, this is around 7 to 10 feet that we excavate, and that ends up being the thickness of our foundation then. And as far as the sizes, they tend to be anywhere from around 50 feet up to 70 feet in diameter, so they're very, very large structures. We pour mud mats, so this is just a thin layer of lean concrete mix. This is really so that we kind of create a level surface to lay our steel reinforcing mats on top of that. So we lay down bearing bars. We have little blocks that they'll place so that we make sure we have enough clearance from the base to that steel, making sure that we protect our steel in the concrete. And then they'll lay down a few bars just to get kind of the foundation built. And then we place the remaining bottom bars. Generally, our designs at least have 2 layers of reinforcing steel in the 2 orthogonal directions. So we have wind that can come at any direction, so we try to make it as symmetrical as possible. And then we set an anchor bolt cage, so that gets pre-assembled so that it's easily to just place in there. You also see in this photo some steel standees, so those are used to place the top mat of reinforcing steel. So here's the top mat of reinforcing steel, again in the 2 orthogonal directions. As far as the sizes of steel, generally they're number 6 bars up to number 11. So, number 11 bar is good size. It's almost 1.5 inches in diameter, so these can get pretty beefy. Then we set the formwork for pouring the concrete. And here's where they're placing the concrete in the foundation. So depending on the contractor, they might choose it to pour it in one pour for the foundation, for the footing, as well as the pedestal. This one is showing doing it in 2 different pours. So we pour the concrete and then let it set, finishing the top of the concrete there. And then we talked about that conduit and grounding that needs to be placed. So generally, this tends to go through the side of our pedestal. So once the base of the footing is poured, they will come in, the electricians will come in and do the conduit layout. And then we'll place the forms for the pedestal and then pour the concrete for that. So here's, I guess, what the ultimate product looks like, which you'll never see again because it all gets covered up. And here's where we're covering it up. So they backfill with the excavated soil if it's suitable to be used as backfill. They come back and do it in layers, making sure that we have enough compaction. They can't just throw it back in there because we need to make sure that we're getting that densified soil and that weight over the foundation. And then they finished grading out the site. You can barely see the foundation now at this point. We also have the transformer pad that needs to be poured. So this is just off to the side of the pedestal, so to extend that conduit out to that. And then they said the base tower section, and then we need to get that layer of grout. So matching up all of the anchor bolts first, and then they kind of hover it above the top of the pedestal, and then get that grout in there, and then place that down and make sure that we have that buffer between the steel and the concrete. And then they come back and tension the anchor bolts, which reminds me, one thing I didn't mention on the anchor bolt design is that just based on the type of material that we use, it actually tends to be more brittle. So what we do is we pre-tension these anchor bolts above any extreme load, and then some that the anchor bolts would ever see. So that's to make sure that they're not seeing that constant cyclic loading on the anchor bolts. So we tension above the extreme load that it would see, just because there does tend to be some loss over time in that tension. And then they'll erect the remaining turbine parts. I don't know if anybody's ever seen these driving on the road, but they are quite large. And then they have to commission the wind farm. So this is something after everything's been constructed. They work with the turbine manufacturer. There's some testing that needs to be done before it can actually go into operation. And I just wanted to touch a little bit on the codes and standards that we use. So as I said, there is no one code that's out there. So just to highlight some of the things that we do use. So first off, there's some different local codes that we need to consider. So county codes, city codes, there might be building permits that are required to build a wind farm. So we need to work with the local officials to make sure that we're meeting their requirements. This is something that tends to not affect our designs a whole lot, but as an example, California does actually have a lot of oversight of their projects, so they get very involved in the design. They want to take a look at our drawings, take a look at our calculations, so it's a little bit different depending on which state you're in. And we do have other state codes, so typically states adopt national codes, but there might be some specific requirements that each state has above and beyond those national codes. So for example, Minnesota, we have a lot of snow, so there's different requirements there. California has a lot of seismic activity, so there's specific requirements to make sure that we're dealing with the seismicity of the site and incorporate that into our design. And then Texas, we have hurricanes, so we need to make sure that we're designing for those loads. And then there's national standards and codes that are out there. So the International Building Code is one that it tends to be adopted by states. We use ASCE 705. That's for determining loads on structures. ACI is used for concrete design. Then we also have this other paper out there that we use to determine some of the soil properties. So that's more what a geotechnical engineer might reference. And there's other international standards that we actually use. So not necessarily ones that have been adopted by codes, other codes in the U.S., but ones that we need to draw on because there isn't something necessarily appropriate in the U.S. So there's a couple of different ones here that we take a look at. Then there's also industry standards. I mentioned IEC, so they're the ones that dictate what loading conditions that the turbine manufacturers need to consider. The Germanischer Lloyd is the one that takes a look at what kind of bearing pressure or bearing length we have on our foundation. We also use this Dittnerski ferry test. I don't know if I'm even saying that right, but we use that offshore code for our fatigue calculations. So as I said, there's not a lot of good references out there on fatigue of concrete. So we use another standard that's out there for us. And then I always recommend that you keep your textbooks. These do come in handy. I honestly never thought I would use my geotechnical engineering book again, but I frequently use that, or I go talk to Rob, because he used to be my TA. So, but we do rely on those. There's books out there to talk about foundation designs that talk about geotechnical engineering. So we do reference those on occasion as well. Just also wanted to touch on professional duty. So as Rob said, he's a professional engineer, I'm a professional engineer. These projects, our foundations do need to be stamped. Our geotechnical reports need to be stamped by professional engineers. So depending on what part of the project we're looking at, you need to have a competency in that specific area to be able to sign off on a project. So individuals need to be licensed, but also businesses need to be licensed, depending on the state that you're working in. Firm needs to be registered in some states. So something that also needs to be taken into account. For us at BAR, we work all across the United States, so we have individuals that are licensed in every state that wind is being put up. So it's not every state, but we do have several different licenses. I mentioned this a little bit, but there are sometimes third-party reviews that happen. So this is something it's really performed on behalf of investors, banks, and owners. So really on the financing side of projects. So before a bank says, here, yes, you can have this money to build your project, they want to know that it's going to stand up. They want to know what is the risk of this project. So they'll hire a third-party engineering company that'll come in and take a look at our designs. Sometimes this happens on the front end as we're in the process of design. Sometimes it happens after the fact, even when a project is built, which can get interesting, especially if the reviewer has comments. So we have had heated debates with other engineering companies out there. There's a lot of engineering judgment that goes into these designs, and people do it differently. So it can get pretty interesting. Then I just wanted to highlight a case study for you guys, give you an example of an interesting project that we worked on. This is the Castleman Wind Project. If you go to our website, you can actually find a little bit more about this project. This is a wind project in western Pennsylvania. It's actually located where there used to be a lot of coal mining. So they wanted to build a project where it was all of mine spoils. And basically, when they're doing the coal mining, all of the material that gets excavated gets dumped into big piles, soil, rock, boulders that get dumped into these huge piles upwards to 90 feet in depth. And they took a look at this. It had great wind. It was on the top of the mountain there, and but it was also where they had all of these mine spoils. And so that's not something necessarily that wind developers take a look at when they're thinking about putting up a project. They see great wind, and they don't necessarily think about the geotechnical hazards that might exist there. So we had to design a foundation to be able to support the wind turbine on this site. So what we did is we used a pile foundation. So again, it was kind of our last resort, but the depths of the mine spoils were very thick that we couldn't do any other sort of mitigation there. So we designed a micropile foundation. It was the first of its kind in the industry, so we actually ended up winning an award for this project. Give you a little bit more description here about the details of the project. So we had 24 8.5-inch diameter battered micropiles. So micropiles are very small piles, as the word indicates. But the reason why we had to use those was because, as I said, these mine spoils had a lot of rocks and boulders in them, and a typical driven pile would not be able to penetrate that soil. So micropiles are used, and the process of how these get installed is basically it's a rotary drill rig that can drill right through that soil and rock. It also, as it's drilling, there's an outer steel shell of the pile that goes down with the drill bit, so it gets advanced as you're drilling. There's some air that gets injected, high pressure air that shoots all of the material that you're cutting through up to the top. And so we drilled it all the way through the mine spoils into the competent bedrock. So as I said, that ranged anywhere from 50 to 100 feet, depending on the site. There were, I believe, 8 different turbine sites at this project that required this type of foundation. We went all the way to the rock and then socketed into that bedrock because the soil above it was not worth anything to be able to rely on for our foundation. So we went all the way into that bedrock, about 15 feet. Then you can see the finished concrete here in this photo of the reinforced concrete pile cap that we put on top of that to, again, tie that into to the tower. So it's a bit of an interesting project, very expensive, but they wanted to build on this site and had great wind, so they were willing to pay the price. So just wanted to recap here. Foundations are really underestimated. It's very critical to the success of a project. Want to make sure that we're designing these appropriately so that the turbines don't fall over. But they get covered up and people don't tend to think about them a whole lot after that. So we want to make sure that we're doing our due diligence up front. It is an integrated design process, so we work directly with our geotechnical engineers when we're doing the design to make sure that we have all of the design parameters and all the correct assumptions that go into our design. As I said, it's a very unusual loading, the fact that we have such a huge overturning moment and not much to resist it. So these structures tend to be quite large. There's also an extensive geotechnical investigation program that needs to occur. And also a rigorous design process. As I said, our calculations get very, very long. And as I said, there's a lot of different codes and regulations that we use because there is not one design code out there. But with that, I guess I did want to highlight, I don't know if you had them read just that chapter of what we have put out, but there are some guidelines that have now been created just in the last year to help foundation engineers in the industry make sure that they're meeting the requirements, meeting the standards of the industry. So it's not necessarily code, but it's a kind of a standard of practice that's been put out there. And we actually had one of our other structural engineers who's been working on this for many, many years, but he was involved in that committee to help write those codes and those standards with other engineers as well in the industry. So with that, I will open it up to any questions. Yeah.
I wonder if there are some trade-offs between technical and
Yeah, well, I mean, as far as the turbine itself, the larger, turbine manufacturers keep making these things larger and larger. You're trying to get more power out of them. There's, offshore wind turbines that can get up to 6 megawatts or maybe even more now. So they keep making them really, really bigger, but from a structural engineering side of things, it gets really complicated. As I said, these foundations can get up to 70 feet in width. Once you're getting a foundation that's that large, the complications of constructing something, even just getting the concrete poured, they need to get several concrete trucks in because you can't draw it out over many hours to pour that concrete. And then when they're doing that, when we get into these massive structures as well, we start having mass concrete issues as well. So the temperature of the concrete might get too high, and it actually affects the long-term durability and strength of the concrete. So I guess I'm not sure if I'm answering your question, but yeah, I mean, there's definitely some trade-offs. If you get more out of your turbine, you're going to pay for it, in the construction and the design. Yeah. Yeah. Here, I should try this. Sorry, guys.
Yeah, I mean, sometimes you might have an issue where the electrical engineer is trying to design a conduit to transfer the power from within the turbine tower out of the foundation. And you have so much steel and rebar in there, and the anchor bolts are set to specific, widths apart to the extent to where those pipes that carry the electrical cables out can't even fit within all the steel that's in the foundations. So that's the only thing I can think of where an electrical engineering issue would come up that could affect the foundation design. So we're working with those engineers to try to find different conduit layouts that can fit within the anchor bolt cage or within the rebar cage. Can't think of anything else though.
Yeah.
Yeah.
Have you ever seen a tower tilt or sink, and then do they try and air it somehow, or
So,
the tower?
question is, have we ever seen a tower tilt or sink? I haven't seen one sink, and thank goodness that's because geotechnical engineers like myself, protect against something like that. We have worked on, or I am working on a project in California where a turbine shut down abruptly and caused the entire tower is leaning over, the foundation is leaning and everything. So we're working on assessing the safety of just having someone go up in that turbine and evaluate what happened mechanically, and then beyond that, figuring out if they can even operate the turbine. So it does happen occasionally, but it's not the norm. Any other questions? Thanks, guys.
Just one other comment, since we are from Bar Engineering. If you guys have any questions about the company too, just in general, this is something that we do, but we also have a lot of other work that we do, hire a lot of civils, mechanicals, electricals. So if you have any questions, feel free.